Philosophers talk to our times towards the theory of common notions. For me, the problem of common notions cannot be separated. When you are talking about the simple common notions, the ones that Spinoza says are easiest initially to define, and relates them back to the attribute of extension and motion and rest, the problem cannot be separated with that deep problem of honesty that besets Spinoza scholarship in relation to Newton. Now, I'm not accusing any Spinoza scholar of being dishonest here, but there is a genuine problem about how you are true to Spinoza's vision of extension in the post-Newtonian world. You see, when you read in Book 2 the infamous, famous, vague, beautiful lemmas and axioms after Proposition 13, where Spinoza is talking about the simplest of bodies, and in about 3 or 4 axioms and propositions, kind of tries to sketch out a theory of physics that will give him the space to say what he wants to say. Now, this theory of physics is clearly rooted in his idea of the infinite immediate mode. It's all about relations of motion and rest. Those ideas that are created immediately from extension. They just give the nature of extension. And as such are a vital part of Spinoza's system that gets called parallelism. So, in the early parts of Book 2, of course, he's talked about the idea of God, the other great infinite immediate mode. And here he is talking about trying to balance up the parallelism. And it sort of works in a lovely, vague way. The problem is with these propositions, for scholarship, but not really for history, is that they are famously, they are clearly Cartesian. And they are following the Cartesian definitions of motion and rest. Now, Descartes doesn't know about differentiation. And his definition then of motion is almost momentum. So in terms of Newton, it's mv. Okay? It is mass, so rest, and speed, so velocity. The good Newtonian scholars in you, those of you who, like me, have been beset by having to teach mechanics for years, will immediately prick up your ears at this point and say, we're on speed here. We're not on velocity. And that, of course, is a profound difference. Spinoza draws no difference between speed and velocity. And unless you draw that difference, it becomes impossible to mathematicalize what he is saying. And therefore, by implication, differentiate it. The differentials become too complicated. So, there's nothing wrong with Spinoza, absolutely, being a good Descartian. But if he is a good Descartian, he isn't a Newtonian or a Leibnizian. And indeed, for me, that's one of the joys of him. It's this innocence. It is impossible, I think, from our side of history, to understand the radicalnesses of Newton's first 3 laws of motion, particularly the second. The first law of motion, that a body remains at rest or at motion until acted, or at constant motion until acted on by a force, is actually directly reconcilable with one of the axioms that Spinoza puts in. I think it's Cartesian. I've got a feeling it's Galilean, actually. Except that Spinoza says simplest bodies will remain at motion until acted on by another simple body, or another speed, or another motion. Newton says bodies will remain at constant speed or at rest until acted on by a force. And a force isn't a motion. Force, on the contrary, is F equals ma, or F is proportional to mass times acceleration. And acceleration is differentially linked to velocity. If you differentiate mv, you differentiate motion, you get ma. They're not the same thing at all. Now, before you go, oh, it doesn't really matter. It flipping does. It just flipping does. Why? The point is about a force is that it can operate across a vacuum. And that's the point of it. Now, Newton in Principia, I checked it yesterday. He is neutral about whether vacuums exist. He doesn't care. But in optics, he implies they do. And certainly one of his acolytes, Locke, was explicitly arguing for vacuums. It's one of his really good arguments. I'm often rather rude about Locke, but his arguments for the conception of a vacuum is fine. Absolutely perfect. Because once you've got forces that can operate across vacuums, you don't need the plenum anymore. You don't need extension, understood as Descartes understood it, as Spinoza understood it, as a floating tank. You can talk about force that can operate at a distance. You can talk about the force of gravity, which is what Newton does, of course, obviously. F equals ma breaks Newtonian, breaks Cartesian physics. More than that, it doesn't really have a space for something that is vital to Spinoza, rest. It's vital for Descartes. This idea that rest is a force. Newton explicitly really breaks with that on his third law of motion. To each force there is an equal and an opposite force, or something like that. Now, why does that matter? Well, it matters because if you think about the famous apple, I know we all go, Newton felt an apple fall and invented gravity. That's not what he did. But what it does do is illustrate the third law, that the force of gravity was operating on the apple when it was at rest. And it was only at rest because there was a second force, pulling it upwards, an equal and opposite force. So that rest itself stops being a thing. It becomes a product of two different forces, pulling in exactly opposite directions. That's part of the jump between difference between velocity and speed, of course. Speed can easily be zero, and velocity will be zero, but it is a zero because there are two different forces operating in different directions upon the said body. The economy here, then, the deployment of the physics is totally different. Now, Leibniz, co-founder of the theory of differentiation, although to be honest with you, he read it from Pascal. One of the things that's happening in the backdrop of Spinoza, one of the things, it is utterly unfair to say, well, he missed it, because he couldn't really have known it, but he did miss it, is that differentiation has already been invented by Blaise Pascal. And so the maths that will allow you to understand force as something separate from the plenum already exists by Spinoza. He just doesn't know about it. Leibniz then, facing this problem, jumps to the monad. He says that the way you've got to understand the differentials, dy by dx, the difference then between acceleration and velocity, is that you have to think of substance as not part of extension at all. We can save the plenum if we actually ironically pull substance beyond extension. It is that which immediately generates extension because there is an infinite number of different substances, each capable of generating their own force, lighting up with it. Force then becomes reconcilable immediately to the world of objects if objects themselves shift or become no longer bodies, but monads. But famously, Leibniz can't do it for everything. He can't do it for gravity. It has enormous problems with the theory of gravity. He calls it an occult force and loathes it. It's why he loses out in the battle of physics and the battle of history, because he asserts rational dogma. Then nothing comes out of nothing, and therefore each motion must have another motion determining it. And therefore, rules out the theory of gravity, which implies action across vacuum. Okay? So the ability to differentiate actually opens up a totally different sort of physics than the kind of physics that Spinoza is clearly reckoning up with. And one's problem as a Spinoza scholar is, what the frig do you do with that? How do you honestly respond? Do you, from the kind of the hints and vaguenesses that simplest bodies mutually could easily be understood as the minutest bodies perhaps, and are clearly always defined in relation to each other, import differentiation into Spinoza, and therefore import force into Spinoza, and just ignore the problem? Do you do that? Now, I spent a professional life, I've alluded to it already, racking my brains, squeezing it into teaching Newton and mechanics at A-level, all the way up to advanced mathematics. I hated it. I can't describe the amount I loathe Newton at the level of laminar and complicated Newton. When you're trying to understand Newton, you get far too close to his mind, and it's really, really uncomfortable, it has to be said. But it is utterly brilliant, and it shatters the pre-Newtonian world of mechanics. It shatters, for that matter, Leibniz. That's why Kant, in the end, won out over Leibniz. Because although actually he does believe in the plenum, the notion of space as some sort of outer sense that I generate sort of almost answers the problems of differentiation. Because it means that it doesn't matter anymore. You can talk about vacuums, and you can also talk about differentials, because it's all my concept anyway. And here, again, do you also ignore the fact that minutest bodies are not the same as simplest bodies? Spinoza, in the lemmas after proposition, in the famous lemmas of the body, really draws no difference, you see, between motions and so forces and bodies. He simply says they're roughly the same. He imports the argument of causes into them. There's no attempt to wrestle with what Leibniz, bless him, wrestles with, which is the agony of what differentiation is, what the differential is. To explain the mathematical mystery. The mathematical mystery is that dy by dx implies, first of all, existent at a moment. Okay, at a moment that is somehow independent, but causes the extension that follows. That's why Leibniz pulls it off to the monad. But worse than that, also implies division by zero. dy by dx is the infinitely small quantity of y divided by the infinitely small quantity of x, approaching infinitely small. The problem, of course, is with maths, if you divide by zero, maths dies. It's over. And so differentiation has to get infinitely close to dividing by zero, while never actually dividing by zero. Now, you can build entire philosophies on differentiation, on why that isn't the same as just straight difference, on how you can tumble into that as a force. Deleuze, of course, does, and Deleuze is always who I'm thinking of in this piece. He absolutely does, and it's brilliant, and it's utterly wonderful, and. But it isn't Spinoza's problem. If that had been Spinoza's problem, well, I actually think he would have dismissed it. Let's be clear about this. I think if he was faced with reading Principia, he would have tried to have argued against it. And I think if he had been faced with, if Leibniz had pulled out Pascal's papers when they had met and said, oh, look, there's this thing called differentiation, I don't think Spinoza would have been able to cope with it, because it breaks with his theory of Descartes. It breaks with the idea of simplest bodies. It has to create something that is different from extension, and he was a good enough philosopher to know it. And so was Leibniz. So what do you do with it? You could, of course, reformat all of extension, make it qualitative, and try and squeeze Spinoza into saying something different, using Bergson, using Leibniz, using whoever you like, and become Deleuze. Absolutely beautiful. It's a great philosophy. But that's not what Spinoza does. It just isn't. So what do? Do you say, as Bennett does, well, we just have to treat Spinoza in his time and not worry too much about it. And admit that his theory of physics, that after the famous letters in the 1660s, by the 1670s, he was being ignored by the Royal Academy. He's desperate to find out what they're saying and what they're doing, and people don't really write to him anymore about it. There's been a war, there's been this, there's been that. And as far as the British Academy was concerned, he was an also-ran in science. I hate to point it out, but it's true. And you just accept that. And we all move on and say, well, the theory of individuality, the theory of individuals understood in terms of different parts exists independently. Or I could say what Spinoza is talking about here is absolute middles. He clearly has bodies positioned in relation to the absolute middle, to the float tank, to field theory. Or, and this is the temptation as a good Spinozian scholar, you wait a bit. One of the things that's happening, I think, in the Baroque, so that's Leibniz, that's Spinoza's, Deleuze's, I'll get it right in a minute, Deleuze's book on Leibniz on the fold, is that it's fairly early on in fractal theory, and Deleuze has just really properly mastered fractal theory. It's there in Thousand Plateaus, but he's really got the hang of it. And he's realised fundamentally this creates a world beyond differentiation, because you can't differentiate a fractal. And actually that fits much better with Leibniz's theories. It fits much better with the kind of the way that Leibniz wants to reconcile the world, and therefore allows you a different angle on Spinoza that could perhaps avoid the entire problem of differentiation, because fractals don't differentiate. I mean, you can differentiate anything, but they don't really differentiate because they have no smallest point. They're defined as that which has no smallest point. You could differentiate them, but it would be open to what it meant, I think is what I would put. And so you can create endless philosophical paradoxes there. It's perfectly possible to do that. Or you could do again, which I sometimes can't resist doing, and saying that I like Einstein. I got put you back on the Spinozian axis because space-time is closer to extension, which it kind of is. And so the issue of vacuum, as Spinoza understood it, was a red herring, because he was he had an idea that was too complicated. In terms of common notions, he could see the common notion that there had to be some cause for everything, but he couldn't see, but he couldn't get it, he couldn't resolve it into an adequate idea, because he couldn't understand the kind of maths that was necessary, the kind of world that was necessary. And that is absolutely true, and leads me on to how I try to resolve that, which is that there is no particular reason why a theory of common notions couldn't include a theory of forces. Really, there isn't. Okay, because the theory of common notions simply talks about the relationships between different elements of the universe and how you can put them in relation one with the other and then use that relationship to develop theories, open up worlds, understand different schemata. You literally can recreate the world then through imminently creating common bonds, or understanding how the common bonds coalesce, cascade through the universe. So force is a classic example. Forces are everywhere in the universe. They are that which explains that which explains why a tree stands and why a planet spins. They are that which understands then what draws the magnet, or binds the soul to the body, to the earth, and means you don't realise that it is spinning and round at all. They are everywhere within the universe, and yet they are nowhere. You don't ever see them. And yet once you understand the theory of forces through experimentation, through learning, through mathematicalization, through further experimentation, you can literally send people to the moon on the theories of Newton. So they work as common notions, as long as you don't get obsessed about the nature of extension as having to be following from the infinite mediate mode. There's nothing in Spinoza that says you have to do that. Common notions create their own unity. And anyway, you can just reform extension as that which puts all things in space, in the absolute middle of each other. That Spinoza then misunderstood that in terms of relations of motion and rest, and only in terms of relations of motion and rest, is of little or no consequence. because the common notion would still be true. And the common notion could certainly be differential. That's fine. That would be all right, I think. I don't see any particular reason why that would be wrong. In the same way the Kantian ideas, same way that Kant would say that there's no particular reason it would be wrong. But it isn't necessarily physical. It isn't physical in the sense that it has an actual existence. Indeed, the point about differentiation is that it doesn't have an actual existence. And simplest bodies do, but through each other, as motion in a float tank. So, for me, common notions allows me to have my cake and eat it. Allows me to be both a Spinozian and a Newtonian without going down the full-on path of having to import differentials directly into simplest bodies, somewhere into the physics. Without having to understand forces in terms of essence or power in terms of essence. So I can keep Newton 1, 2 and 3 and yet allow Spinoza his Descartesianism. It's a paradox. When I make the argument, and at the end of it I suddenly go, well, he's Deleuze right after all. And he isn't. He really isn't. But the common notions mean that the argument doesn't matter. That's why I think I'm so interested in them. It is to try and honestly respond to this deep problem that Newton gave Spinoza scholarship, unintentionally. A problem that doesn't have a straight solution. Perhaps it has no solution. But I feel has to be honestly faced. And merely just to deny it or to say that Spinoza can have differentials, it merely shows you don't understand really what a differential is in the end, for me. I'd give you 0 out of 10 if you said that in a mechanics exam. And that's always the paradox I've lived with, being both a philosopher and a teacher of Newtonian mechanics.